Now here is another LeetCode problem. This is 133 clone graph. Okay. Given a reference of a node in a connected undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value integer and a list node of its neighbors. Test case format. For simplicity, each node's value is the same as the node's index, one index. For example, the first node with value 1, the second node with value 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be the first node with value 1. You must return the copy of a given node as a reference in a clone graph. Alright, so let me reread the problem here. Given a reference of a node in a connected undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value in and list a node of its neighbors. Alright. Okay, so I think the problem is quite obvious. We just need to create a copy of the node. Okay, now I think it's better to just directly look at the example here. So example 1. We have 1 connected to 2 and 4, and then 2 and 4 connect to 3. So you can't return the same graph. This looks like the clone, the nodes are new, now looks the same. The nodes were cloned, but the graph is messed up, doesn't have the same connections. Alright. So basically we want to return the exact copy. Okay. So in the first example, we have 1 connects to 2, 1 connects to 4, then 2 and 4 connects to 3. Example 2, there is, what is that? So there's 1 node, okay. So it's empty node. So there's 1. Example 3, there is nothing. So we return nothing. Alright, so I think it's pretty obvious in here. So there is possibility that there is no node at all. So okay. There are no repeated edges. Hold on 1 second. How does it identify a node? So node file is unique. Okay. And there are no repeated edges and no self loops. So I think that is something that is worth clarifying. So one way to ask about it is to ask like is file unique? So it says yes, file is unique. How about I think sub loop is fine, right? So the server it points to itself. Okay, so repeat edges, no, and then 3 self loop, also no. Graph is connected and all nodes can be visited. Starting from the given node, and I guess that is not this. So I think we just directly work with the implementation here. So the idea, I think I got the problem now. I think it's time to think of some possible solution. Think of a possible solution. So you're given a node. So I think what we can do is that first of all we create a, let's say, a dictionary, because its node is unique and the value is unique, so we can use the value as kind of an ID towards the node for the node. So some findings. Let me put down some findings here. Not dot file. So not dot file is an ID of a node. Now second, so I'm trying to think of the solution while looking at the example there. So I think what we can do is if we add a neighbor to 1, then we also can also add 1 to that particular neighbor. So add x to neighbor and add neighbor to x at the same time. So what we're going to do is for each of the node, we're gonna add the neighbor on both sides. Okay, I think another things that we can do here is that go through each node. And then so let's say we go through each node and then we could say add the neighbor. Now so the node class is a very simple one. There is no API to add a neighbor. So what we're gonna do is we need to manually add it into the list. Okay. I think another question I could ask is that whether the list has to be sorted in the same order or not. But I think it should be answered here. So it says okay, so at the adjacency list is a collection of unordered lists used to represent a finite graph. Okay, so it doesn't have to be ordered in any way. Then in this case, what we're gonna do is, how about we make a dictionary, and then as we found a node, we keep creating a new node for it using the file as key, and then we add it into our dictionary. Okay, I think it's better to work on an example here. So if we have like 1, now we see that 1 has a neighbor of 2 and 4, so we create 2 and 4, and then we add the neighbor. So 2, we add 2 to the neighbor of 1, and then we add 1 to the neighbor of 2, and also one has a neighbor of 4, so we add 4 to neighbor of 1, and then we add 1 to the neighbor of 4. After that, we mark 1 as done. Okay, so 1 is done. Let me put a check mark there. So, check mark. So now we were on 2. From 2 we see that there is 1. But 1 is done, so okay, so let me write it down here. So 4. Because 1 is done, we don't need to add it into our neighbor. But 2 as a child have a neighbor of 3, so we add 3. 3 is not in the dict, so we add a new one. And then we add 2. And now let's 2 is done. Then move on to the 4. 4 has 1 and 3. 3 is done. And then 3 is also done. So I think that's how we're gonna do that. Alright. So the step is that 1, add node to dict. 2, add neighbor. Then add into let's say visited. Okay, I think that should work. I would like to start programming now, unless there is a further optimization that you would like me to explore. Okay, so I think it's good. Now let's go to the solution. So you're given a node. Let me just create a dictionary. I'm gonna call it clone. So clone is a dictionary with initializing as an entity, and then okay, I think I need another set here. So found. Now found is a set that is not visited yet. Or I would say, let's just call it to do. So to do, I'm gonna add the current node. So set current node dot found. Okay, and then how about call it done set. So here I'm gonna do a while to do. I'm gonna look through all the files. Guess it just store the node. Okay, let me think about it carefully. So I need to know the node that is not copied yet. So how about I store the node into the to-do. Yeah, I think that makes more sense. Okay, let's do that. Let's just, instead of adding the value, we add the node directly. So node equals to do dot pop, and then we are gonna go to all the child. Not in clone. Then we create a clone of the node. So clone of node dot file equals a new node of the file. So node dot file. And then we are gonna check all the neighbors for node neighbor in neighbors in node dot neighbor. Then we check if neighbor. Okay, sorry. Instead of node, we need to check the file. Not in clone. Then we create the clone. Neighbor.file equals node neighbor dot file. Okay. Now after we create the neighbor, we need to add it into our neighbor list. Actually, first of all, we could check whether it is in the done set. So if neighbor dot file in done, then we just continue. Okay, so this part should be before the if, and then after that we need to add the neighbor to it. So clone or not dot file dot append the clone or neighbor dot value, and vice versa. We add it into the neighbor. So neighbor dot file dot append clone of not dot file. Now we also need to add it into our to do dot add the clone so it should be the node, I mean the original neighbor. Okay, so neighbor, so that the next time we check the neighbor of the current node, then we add done. So done dot add node dot value. Okay, before we add to do, we need to check if it is done or not. Okay, so we actually have checked it before. Alright then. Yeah, I think that's all. Is it? Then we finally return the clone of 1. So now let's try our example there. So to do is 1. Now we have done. So while to do, we pop it. So current node is not in the clone. So we create it. And therefore all neighbor, which is 2 and 4, it is not in the done and it is not in the clone. So we create it 2 and 4. Okay, we first create 2 and then colon dot to append. So we create the 1.22, 2.21. Then we have created the edge. So 1 and 2 are now connected. Then we add to do into the neighbor. And we add neighbor to do. So the next time we need to explore 2 and also 4. So 1, 2, 4 are copied, are cloned and connected. So done, we have 1. Now we work on 2. So we pop 2. 2 is in clone. Then we check the neighbor has 1 and 3. 1 is done. So we continue. 3 is not in clone, so we create it. And then after we create that, we're gonna make the connection to 2. Okay, now we add 3 into the to do, and then we add 2 to the done. Now we pop 4. 4 is in the clone, now the neighbor is 1 and 3. So 3 is not done, 1 is done. So we create 3, 4 to 3, we connect them. And then we add 3 to the to-do, which is already there. And then 4 is done. Continue with 3. Now 3 is in clone and the neighbors are all done. So we add it to done 3. Now it is empty. Okay, so it works. Second example. There is only 1. So we create 1. And then it's done. Number 3, there is nothing there. To do is empty. Clone is empty. So to do is empty, then we return. Okay, Python dictionary can return none. I think we can call get. So clone, instead of clone 1, we can return clone.get 1, none. Okay, I think that should work. Now let me quickly put it into LeetCode to make sure I have to make sure I got it right. So let's write the clone is a dictionary. To do is a set. I think we better just check if there is no. If not node, then return the node. Otherwise, we add the set of the node itself as a to do, and then done is an empty set. Now the value is to do not equals to do dot pop. If not dot spell, not in clone, then we create one clone, no, not dot spell equals not of the file. Okay, now the neighbor. For neighbor in not the neighbors. So we are gonna check if the neighbor is done. If neighbor dot found in done, continue. Otherwise, if neighbor dot found not in clone, then we create it. Neighbor dot found equals not neighbor dot found. Now we add the edge. Clone not dot found dot append the clone of neighbor dot found. Now we add the same to the opposite side. Yep. And then at the end we call it, don't forget to add it into to do dot add neighbor, and then done dot add the node dot now. Then we return clone of one. Okay, let me try to run this. So node has now a previous append clone dot neighbors. Sorry about that. Oops. We append it into the neighbors. Yep, we got it right. So let's try to submit it. And we got accepted. So I think that's it. Let's look at some other example of submission, which is much more efficient, turns out. The solution clone graph DFS current a curve in clone, then return clone of curve. How does this work? DFS of node. If node in clone, then return clone. Copy equals node out. So we create the copy of it and then clone, and then we append into the neighbor. Okay. I see. But how does it know that it won't do it repeatedly? I think that is the interesting point. I see, so it use a public dictionary to do that. Yeah, I think that makes sense. That is definitely more efficient. Yeah, so the clone dictionary there makes sure that it is not creating a copy of any existing node. Yeah, I think that could work too. Although I think it's much more difficult to come up with this solution. Uh, yeah. Actually, this is kind of a recursive solution or recursive implementation of what we are doing. Yeah, if you think about it, this is kind of the same implementation, but it is the recursive version. So anyway, let's look at some more examples. Okay, and this is not using DFS, but it's quite efficient. Clone, clones, queue.append neighbor, and stop neighbor.append the node. And see, so this is taking care of each node one by one. Hold on, this is using deck, pop left, neighbors, and then neighbor not in clone, we created, and then append it. See. Actually, this is similar to what you're doing, right? So we pop it if it's not in clone. Clone.current. Okay. Curious, how about I resubmit it and see if it is first directory? Okay, still 48. Yeah, I think it's more or less the same as everyone. It's just that my solution is, I think it's easier to come up with, and then in here it's kind of much more tidy. So here I think an important note is that if the solution only add to the queue if it is the first time we seen that particular node. Otherwise, we have seen it before, or we have added to the queue, so we don't even need to redo that. Yeah, I think that simplifies the solution. So that is great. But, I'm gonna keep my solution there because it looks like it's more or less doing the same thing. Okay, so thank you everyone. We will stop here.